ABC of Medical Biochemistry, Professor Dr. Mozammel Haq, MBBS, Phil Biochemistry, FCPS Biochemistry, Professor Department of Biochemistry, Bangabandhu Sheikh Mujibur Rahman Medical University, BSMMU, Dhaka, Bangladesh. Former Professor of Biochemistry, Dhaka Medical College, Sir Solimullah Medical College. ABC of Medical Biochemistry, Gateway to Biochemistry, Chemistry of Carbohydrate, Chemistry of Protein, Chemistry of Lipid, Biological Membrane and Membrane Transport, Chemistry of Enzyme, Chemistry of Nucleic Acid and Nucleotide, Chemistry of Digestion and Absorption, Chemistry to Metabolic and Biological Oxidation, Carbohydrate Metabolism, Protein Metabolism, Lipid Metabolism, Integrated Metabolism, Renal Biochemistry, Fluid and Electrolytic Balance, Acid-Base Balance, Molecular Energy, Genetic and Engineering, Recombinant DNA Technology, Nutrition and Vitamin, Hormone Biochemistry and Clinical Endocrinology, Clinical Biochemistry, MCQ, Reference Index. Chapter 1, Gateway to Biochemistry. Solution. Definition. Solution is a homogeneous mixture of two or more substances, solid, liquid, or gases, contributed uniformly among each other. Homogeneous mixture. It is the mixture of two or more substances showing all through same consumption. Heterogeneous mixture. It is the mixture of two or more substances showing different composition in different parts of the total mixture. Solvent. Solvent is the component of a solution which forms larger portion of that solution. Physical state of that solution must be same as the physical state of solution. Solute. Solute is the components of a solution which form mirror protein of that solution. Solutes are held in solution by the solvent. For example, 0.9% NaCl solution. Here water is solvent because it represents the major portion and its physical state is liquid like the physical state of solution. Here sodium chloride is solute because NaCl represent minor portion of solution and it is kept in solution by water. Heterogeneous solution. It is a heterogeneous mixture of solution and solvent where solutes exist as aggregates of molecular, for example, solution of protein in water. Homogeneous solution or true solution, molecular solution. It is a homogeneous mixture of solute and solvent where solutes exist as the molecules ions. Here solutes are crystalloid with size less than 1 nanometer and do not sediment out, passing them through filter paper or semi-permeable membrane. In fact, a solute means mixture of two or more substances. It could be homogeneous or heterogeneous, but traditionally by the term solution we like to mean that homogeneous solution that is likewise known as the true solution. Concentration of a solution. It is the amount of solute present in a given quantity of solvent or solution. Atom. Atom is the smallest particle of a substance that takes part in chemical reaction. An atom consists of nuclei composed of protons, positive charged particles, and neurons, particles without any charge, surrounded by electrons, negative charged particles. Element. Element is a substance made out of only one kind of atom. For example, sodium. Compound. Compound is a substance that made out of two or more different kinds of atoms. For example, water. Atom weight. AW. Atom weight is the sum of number of protons and neurons of an atom. It indicates a number that expresses how many times an atom is heavier than an atom of hydrogen. For example, atom weight of sodium is 23. That means an atom sodium is 23 times heavier than one atom of hydrogen. Molecule is the smallest particle of an element or compound that can normally exist freely. For example, atom weight of sodium is 23. That means an atom sodium is 23 times heavier than one atom of hydrogen. Molecular weight. Atom weight then molecular weight MW. Molecular weight is the sum of the atomic weight of all atoms in a molecule. It indicates the number that expresses how many times a molecule is heavier than one atom hydrogen. For example, molecular weight of one hydrogen, one water H2O is 18, 2 into 1 plus 16. That means one molecule water is 18 times heavier than one atom hydrogen. Equivalent weight, EQ weight. Equivalent weight of a substance is the number which indicates how many parts by weight of that substance will combine with or displace one part by weight of hydrogen, or 8 parts by weight of oxygen, or 35.5 parts by weight of chloride. For example, EQ weight of calcium is 20. That means 20 parts by weight of calcium will combine one displace one part by weight of hydrogen. Mole, symbolized as mole. It is the gram molecular weight of a substance if compound, or gram atomic weight of a substance if element. Molecular weight or atom weight of a substance expressed in a gram. For example, molecular weight of calcium is 40. So 1 molecule calcium is 40 grams calcium. Molecular weight of sodium is 23. Molecular weight of H2SO4 is 98. Molecular weight of NaCl is 58.5. Molecular weight of H2O is 18. Molecular weight of CaCl2 is 111. Symbolized as EQ. It is the gram equivalent weight of a substance. Equivalent weight of a substance expressed in a gram. For example, equivalent weight of calcium is 20, sodium 23, H2SO4 is 49. Relation between molecule and equivalent. Equivalent mole plus valency, osmole, symbolized as OSM. It is the amount of osmotically active substance in gram, which is 1 liter solution with the water exerts osmotic pressure 22.4 atmospheric pressure and depresses the freezing point of water by 1.86 degrees Celsius. Osmotically active substances means any substance which can be exert osmotic pressure in solution with water. Relative small amount of highly osmotic active substance, for example Na2 plus glucose etc., represent 1 osmole compared to osmotically less than active substance, for example protein. For less active substance, relatively a big amount equals to 1 osmole. Osmole is used as the unit of measurement for osmotically active substances. Relation between mole and osmole. Mole, the number of particles given by each molecule in solution by dissociation. Units of measurement. Expression of concentration of a solution, percentage by weight, percentage by volume, molarity, molality, normality, osmolality. Relation between molality and normality. Relation between molality and osmolarity. Practical use of units of measurement. SI unit, system international units. Traditional system of measurement is CGS system and MKS system. Different people use different systems, leading to the reporting of laboratory data in different scales, which makes the issue problematic. To overcome this problem, IUPAC, International Unit of Pure and Applied Chemistry, and IFCC, International Federation of Clinical Chemistry, in 1967 proposed a uniform standardized international system of unit called SI unit for presentation of laboratory data, who adopted in 1977 in its 30th World Health Assembly and finally recommendation published in 1979. This is known as the SI unit. There are three classes of SI units. SI base unit. These are 7 base units for 7 fundamental dimensional independent physical quantities. For example, quantity name of unit symbol, length meter m, mass kilogram kg, time second s, temperature Kelvin K, amount mole, current ampere A, luminous intensity candela CD. SI units. These are derived mathematically from 2 or more SI base units. For example, area ms square, volume m cube, concentration kg per liter, mole per kg, pressure Pascal, energy joule, supplemental unit. For example, minute, hour, day, millimole, mosm, meq, etc. Interconversion of traditional units and SI unit. Substance WMAM SI unit. Osmolarity and tonicity of solution. Osmolarity is the total concentration of all osmotically active solutions, both permeable and non-permeable, per liter solution. So osmolarity is determined by the total solute concentration in a fluid compartment. Tonicity is the concentration of only non-permeable osmotic active solutions per liter solution, which generate osmotic pressure to cause osmosis, water movement between two solutions when they separate by semi-permeable membrane. Creation of transmeable solution, concentration difference and osmotic gradient, osmotic pressure difference between two solutions across a semi-permeable membrane is not the function of osmolarity but is the function of tonicity, since tonicity indicates the concentration of only non-permeable solutes, not permeable solutes. Permeable solutes quickly equalize their concentration across a membrane, causing no transmembrane solution concentration difference osmotic gradient, but non-permeable solutes cannot do that. So many permeable solutes contribute to the total osmotic solution by not to the tonicity of solution, since they cannot create transmembrane solute concentration difference and osmotic gradient. Since tonicity determines the transmembrane solute concentration difference and osmotic gradient, it generates osmotic force and causes movement of water, osmosis. For low concentration solution, low osmolarity, the high concentrated solution, high osmolarity across the membrane. So osmolarity is the physical property of a solution that depends on both permeable and non-permeable solutes, whereas tonicity is the physiological property of a solution because tonicity determines whether osmosis will occur or not and depends only on the non-permeable solutes. To increase ECF tonicity, the solutes must be confined to the ECF compartment, unable to go into ICF compartment. So these solutes increase osmotic pressure of ECF and draw water from ICF to ECF to establish osmotic equilibrium. Tonicity is otherwise regarded as effective osmolarity since it determines whether there will be osmotic or not by creation of transferable solute, concentration difference and osmotic gradient. Therefore, non-permeable solutes NaCl, mannitol, sorbitol, glucose that determine tonicity are considered as effective osmol, whereas permeable solutes, area non-alcoholic, etc., are considered ineffective osmol because these are not concerned with the creation of transferable osmotic gradient and osmosis. Therefore, tonicity is the net osmolar gradient across the cell membrane that drives osmosis, water movement. Isoosmotic versus isotonic solution. Solutions having some osmolarity total solute concentration are known as isosomatic solution, and solutions having some tonicity non-permeable solute concentration are known as isotonic solutions. If two solutions differ with respect to tonicity respect of their osmolarity, water movement will occur from hypotonic to hypertonic solution. But if the two solutions are isotonic to each other, they will osmose between solution, whatever may be process osmolarity status. Then initially two solutions are not osmotic but isotonic, so no osmosis will occur. Tonicity of solution has its effect on cell volume. Clinical importance of tonicity of solution. Surface tension. A molecule in the interior of a liquid is completely surrounded by other molecules and attract equally in all different but on the same on the surface molecular of liquid. However, there is result attraction inwards and because of this inward pulling, the surface of the liquid always tends to contact to the smallest possible area. Surface tension is the force acting along the surface of a liquid by which surface molecules are held together. Application of surface tension. Digestion of fat. Bile salt decreases the surface tension and dietary fat and emulsifies big fat globules into minute particles. This increases surface area of fat and affects digestion. Surface and lung function. Surfactant and lung function. Chemical composition of body. Proximally in 70 kg adult, water 60%, lipid 15%, carbohydrate 2%, protein 15%, minerals 8%. Elementary composition of body. Proximate carbon 50%, nitrogen 8%, other 6%, oxygen 20%, calcium 4%, hydrogen 10%, phosphorus 2%. Major biomolecules of the body. Protein, amino acids, glycogen, glucose, DNA, deoxyribonucleic acid, RNA, ribonucleic acid, lipid. Protein, glucose, DNA and RNA and biopolymers, but lipids are not biopolymers. Biopolymers are substances composed of large number of small or identical monomeric units. Different biomolecules and their building blocks, monomers, present in biological system can be broadly classified into crystalloid, amicron and colloid, submicron, depending on their size. Crystalloid are substances with size 1 nanometer which can pass through semi-permeable membrane, for example electrolytes, minerals, glucose, amino acids, etc. Colloids are substances with size 1 to 100 nanometer which cannot pass through semi-permeable membrane, for example protein, glucose, stretch, etc. 90% of the organic matter of living tissue is celluloid. Microns are solute having size more than 100 nanometer, and they form sustainable emulsion of suspension with water. Comparison of true solution, colloidal solution, and suspension. True solution, colloidal solution, suspension. True solution. Solution size less than 1 nanometer called amicrons or crystalloids. Homogeneous. Solutes exist as molecule or ion. Solute negative segments. Out of standing. Exert high osmotic pressure. For example, normal saline. Colloidal solution 1 to 100 nanometer called submicrons or colloid. Heterogeneous. Solute exists as aggregates of 100 to 1000 molecules. Solute never sediments out on standing. Exert very low, negligible osmotic pressure. Albumin solution. Suspension bigger than 100 nanometer called microns. Heterogeneous. Homogeneous was only the true solution. Solution exists as aggregates of millions of molecules. Solute sediments out on standing. Exert on osmotic pressure. Dialysis. It is one of the methods used to separate colloid and crystalloids from the mixture. The principle of dialysis is based on the fact that crystalloid substances in solution can pass through permeable membrane, while colloid particles cannot. Semi-permeable membrane used in dialysis may be parchment membrane, cell phone membrane, cellular membrane, cellulose nutrient, cellulose acetate, etc. These are called dialyzing membrane dialyzer, usually in the front of an elongated tube or a bag. Dialyzing membrane acts as a sieve, retaining the longer particles. Mixture of crystalloids and colloid in place inside the tube or bag of dialyzer, and then suspended in a vessel containing dialysis fluid. Dialysis fluid is prepared without the crystalloid substances, which are to be separated. The crystalloid particles form the mixture will diffuse out to the dialysis fluid through the dialyzer down their concentration gradient, but colloids will retain within the dialyzer. Dialysis fluid is changed either periodically or continuously as the crystalloid particle diffused out from the interior of the dialyzer into the surrounding dialysis fluid. Importance of dialysis. It is used as artificial kidney for treatment or renal failure. In renal failure, the crystalloid uremic toxins, for example urea, creatinine, etc., accumulate in the blood since kidney fails to exert them. So by the process of dialysis, it is possible to remove this uremic toxin from the blood, which allows the patient to renal failure to survive. This is used for treatment of hyperkalemia. Law of mass action. Importance use of the law of mass action. It explains the basis of biochemical reaction and predicts the reaction rate. It expresses the concept of pH. Page 28. Discussion of H2O and pH. Henderson-Harris-Welch equation HHE. This is the equation that explains the quantitative relationship between the pH of the weak acid and its associated constant. Importance of use of Henderson-Hasselbalch equation HHE. In clinical biochemistry, HHE is used to spell out the concept of acidosis and alkalosis. According to the HHE, when base salt decreases and acid increases, pH gradually decreases, leading to acidosis, in which base salt increases and acid decreases. pH gradually increases, leading to alkalosis. Determined blood pH and elevated the acid-base solutes of patients. S is the internal consistency of acid-base parameters of blood, pH, PCO2 and HCO3, measured clinically in a patient for current interpretation and diagnosis. It is used to determine the pH of weak acid and indicators. It is used to determine the pH of buffer solution, and its qualify the buffer components need to prepare the buffer solution different pH. It is used to predict the behaviorability of drug and calculate the abundance of ions from forms of acidic and basic drugs at a particular pH. Gibbs-Donen effect and Gibbs-Donen equilibrium. Gibbs-Donen effect. It is the effect of and distribution of diffusion ion between two sides of the semi-permeable membrane due to the presence of non-diffusible ions on the side of the membrane. On the side containing non-diffusible ion, diffusible contains ion will be more concentrated, and on opposite sides same charge diffusion ion will be more concentrated. Solution 1. Gibbs-Donen equilibrium. Then isomer. Importance of Gibbs-Donen equilibrium. Generation of resting membrane potential RMP and maintenance of RMP. Maintenance of different ion concentration in biological fluids. For example, due to non-diffusible negative charge plasma protein, concentration of plasma cations are 2% higher than those in interstitial fluid. Conversely, concentration of ions in interstitial fluid are slightly higher than those in plasma. Isomer definition. Isomers are substances having some molecular chemical formula but different structures. Isomers have substances having same molecular formula and identical structure from but different spatial configuration around one or more carbon. Isomerism is the process of formation of isomers. Types of isomers: structural isomer, stereoisomer, geometric isomer, for example cyst variety and trans variety. Optical isomer, structural isomer. These are the substances having some molecular chemical formula but different structure. These types of isomer differ with respect to physical and chemical properties. Stereoisomer, space isomer. Substances having some molecular formula as well as identical structural form but different with respect to the spatial configuration of atoms of groups around one or more carbon. These types of isomers sometimes shows identical physical and chemical properties. Spatial configuration means types of stereoisomers. Epimers, optical isomers. Isotope definition: atom with same atomic number of protons but different atomic weight, number of protons plus neutrons. Atoms of same element with different atomic weight due to different neutron number. Types of isotope: unstable isotope, radioactive decay. It is the spontaneous recombination disintegration of an unstable isotope of a definite element in the attempt to become a stable isotope with simultaneous emission of radiations alpha, beta and gamma, forming a new element. Mechanisms of radioactive decay: alpha decay, beta decay, positive beta decay, alpha decay. It occurs in heavy atoms number 70 or more, and here alpha particles are emitted from the radioactive nucleus. Beta decay. It occurs in atoms in atomic number 60 or less. And here beta particles are emitted from the radioactive nucleus. Positive beta decay. It occurs in artificial isotopes, and here positive beta particles are emitted from the radioactive nucleus. Radioactivity is the spontaneous emission of accelerated particles. Radiation from unstable isotope or radioactive decay. Half-life of radioactive isotope. It is the time required for radioactive isotope to reduce to radioactivity to half and its initial value. Carbon 5760 years, hydrogen 12 years, cobalt 5.3 years, chromium 28 days, phosphorus 14 days, iodine 8 days, technetium 8 hours. Properties of alpha ray, properties of beta ray, properties of gamma ray. Clinical use: radio sensitive tissue, and they are mostly rapid diversing tissue. Radiation hazards, disadvantages of radioactive isotope: protons, acid, and base, alkali, amphoteric substances. Properties of alpha ray: it is a stream of alpha particles, positively charged and readily absorbed by matter, so cannot penetrate the matter. Properties of beta ray: it is a stream of beta particles, negatively charged and less absorbed by matter, so have a high permeability. Properties of gamma ray: it has high frequency with short wavelength, carry no charge and less absorbed by matters, so have high permeability. Alpha, beta, and gamma ray interact with matter to produce ion pairs, and so that they are called ionizing radiation. Clinical use, clinical importance of radioactive isotope. Diagnostic use of isotope for diagnosis of disease. For example, iodine uptake test for diagnosis of thyroid disorder. Radioimmune assay for hormones for diagnosis of hormone disorders. Organ scanning, for example, bone scan, brain scan, thyroid scan. Absorption test, for example, the iron, vitamin B12, etc. Isotope renogram for measurement of GFR and renal clearance. RBC for span measurement. Therapeutic use, for example, radiotherapy in treatment of malignancy. Use in tracer technique. Isotopes are used as tracer in metabolic studies to outline the metabolic pathways. Measurements of volume and spaces, for example, ECF volume, blood volume, plasma volume, etc. Measurement of regional blood flow, for example, cerebral blood flow, coronal blood flow, renal blood flow, etc. Sterilization of medical instruments. Radiosensitive tissue. These are mostly rapid diversing tissue. Bone marrow, gonads, lymph node, skin, and intestine. Radioactive hazards. Disadvantages of radioactive isotope. Immediate hazards: bone marrow, depression, and immune suppression. Damage to interstitial mucosa causing diarrhea and malabsorption. Baldness, raw and scaly skin. In pregnancy, fatal growth retardation, congenital malformation and fetus, fatal death, neonatal death. Delayed hazards, for example, carcinogens, sterility, cataract. Genetic effects, for example, DNA damage and mutation. Proton H is the hydrogen atom with the neutralizing electron removed. Acid. Acids are proton donors in aqueous solution. Acid contains hydrogen atoms and capable to release hydrogen ions in aqueous solution. Acids may be molecular acids, with positive charge NH4 plus or negative charge H2PO4, or without charge HClH2SO4. Conjugated base of an acid in the remaining anatomic part of an acid after removal of proton. Acid conjugate base HCl minus H2CO3 HCO3. Lactic acid lactate H2SO4 SO4 2 minus. A strong acid is the acid which rapidly and completely ionizes into H plus and its congenital base ions. Weak acid is the acid which slowly and partially ionizes into hydrogen ion. Degree of dissociation ionization of substance is called dissociation. For strong acid, degree of dissociation and dissociation contact K is high. In case of strong acid, the congenital base shows less affinity to proton, because of which they can rapidly and completely ionize to proton. Difference between strong acid and weak acid: ionization complete, partial, free activity high, low, dissociation constant high, low, pK value low, high, conjugated base weak, strong, buffer activity absent, present, base alkali and amphoteric substance. Base are proton acceptors in aqueous solution. Bases may be charged particle, for example Cl, HCl3, or may be without charged, for example NH3. Strong bases are those which have greater tendency to accept proton. They bind rapidly and strongly with proton, so quickly remove proton from solution. Alkali are metallic hydrogens of alkali metal, for example Ca and which are solution ionized to hydrogen ions that can bind hydrogen to form H2O and thereby can remove hydrogen ion from solution, for example NaOH, KOH. Alkali are metallic hydroxides of alkaline metals, for example sodium, potassium, which is solution iodized to hydroxylized ions OH minus that can bind H plus from H2O and thereby can remove hydrogen ions from solution, for example NaOH, KOH. Strong alkali are those which rapidly and almost completely ionize to hydroxyl ions OH minus that quickly remove hydrogen ions from solution, for example NaOH, KOH. Weak alkalis are those which slowly and partially ionize to hydroxyl ions OH and that slowly remove hydrogen ions from solution, for example CaOH2. In fact, all alkalis are also regarded as base, but all bases are not alkalis. In spite of that, base and alkali are often used simultaneously. Amphoteric substance, ampholyte. These are the substances which can act both as acid as well as base in different solutions. H3PO4, H3PO4, HPO4 2 minus H2O, H2O plus H plus, SOH2, so H2PO4, HPO4 2 minus and minus 1 agetta chilo, and H2O are ampholytes. Free acidity, natural acidity. Free acidity is a solution is instant hydrogen ion concentration measured without any manipulation. For equimolar concentration of strong acid 10 mole per liter and weak acid 10 mole per liter, the free acidity will be very high in strong acid solution compared to that in weak acid solution, because strong acids are completely dissociated with weak acid are partially dissociated into hydrogen ions. Titratable acidity, total acidity. Titratable acidity is a solution is its total H plus concentration that would be if the acid was allowed to ionize completely to hydrogen ion following its titration with alkali. For equimolar concentration of strong acid 10 mole per liter and weak acid 10 mole per liter, the total hydrogen ion concentration of both the concentration will be the same 10 mole per liter. At the end of complete ionization following the titration with alkali, very small amount of weak acid usually ionized to H plus and majority fell into ionize during titration. When alkali is added to the medium, the H plus concentration of the medium decreases with facilitated with ionized weak acid and ionized comparability to H plus. Equimolar concentration of strong acid and weak acid differ with respect to different acidity, more with strong acid, but they are same with respect to the tetrable of total acidity. pH of solution. pH is the negative logarithm of hydrogen ion concentration of a solution. When H plus concentration is expressed in terms of molarity mole per liter, for example, 10 to the power minus 7 is 7, 10 to the power minus 8 is 8, 10 to the power minus 3 is 3. pH scale of solution. It is a mathematical scale showing interrelationship among the different values of H plus, OH minus, pH and pOH of aqueous solution of 25 degrees Celsius when the ion product of water is K is 10 to the power minus 14. Isoelectric pH PL. It is the pH at which biochemicals, for example protein, amino acids, etc., exist as Zwitter ions, dipolar ions, possessing same amount of positive and negative charge on their surface with net charge 0. So at isoelectric pH, biochemicals are electrically neutral and exist as Zwitter ions, not capable to show extra electroporetic mobility, less soluble in water, rapidly precipitate of solution. Why albumin exists as an ion in plasma? The isoelectric pH of albumin is less than the pH of plasma 7.4. Therefore, this plasma albumin is exposed at a pH above the isoelectric pH. So, albumin releases protons and attain negative charge ionic form. Importance of isoelectric pH. It is used as the basis of develop different procedures, for example electrophoresis, for separation and qualification of proteins and other biomolecules. Buffer definition. Buffer is a mixture of weak acids and conjugate base that tends to prevent the marked change of pH of a solution when moderate amount of rich or base is added. Acid or base is added. Buffer mixture of weak acid and salt with strong base that tends to maintain the pH hydrogen ion concentration of solution within normal range in spite of the addition of acid or base to a solution in a moderate amount. Mechanism of buffer action. Buffer acts by converting strong acid into weak acid and strong base into weak base and thereby minimize the effect of strong acid or weak acid on pH of a solution. The isoelectric pH of albumin is less than the pH of plasma. Therefore, its plasma albumin is exposed at a pH above the isoelectric pH. So, albumin releases proton and attain negative charge ions from. Importance of isoelectric pH. It is used as the basis of develop different procedures, for example electrophoresis, for separation and qualification of proteins and other biomolecules. Buffer definition. Buffer is a mixture of weak acid and conjugated base that tends to prevent the marked change of pH of solution when moderate amount of acid or base is added in. Buffer is a mixture of weak acid, and its salt with strong base that tends to maintain the pH of hydrogen ions concentration of a solution within normal range, in spite of the addition of acid or base in a solution in moderate amount. Strong acid and base can markedly affect the pH of a solution by dominating or removing large amount of proton pH plus in solution. If strong acid or strong base are converted into the weak counterparts of counterpart, then there will be negligible disturbance of pH plus concentration of solution, because weak acid and weak base undergo negligible dissociation. In fact, buffer acts through neutralization of added acid by buffer base and added base by buffer acids. NaCl strong NaHCO3, weak H2CO4 and NaCl. NaOH is strong plus H2CO4 is to NaHCO3 weak plus H2O. Buffer acts by dominating protons into the solution by the buffer acid when there is proton deficient, and by removing protons from the solution by the buffer base when their proton exists. Buffer and Henderson-Hasselbalch solution. Mechanism. Maximum activity of buffer. In buffer pair, pH is fact presents the pK value of buffer acid. In buffer pair, conjugate base and the salt that of base are conceptually synonymous. Maximum activity of buffer. In a buffer pair, there are two components, weak acid and its conjugate base salt. The weak acid acts by dominating protons into the solution in case of proton deficit, acid base or alkali excess, whereas the conjugate base salt acts by removing protons from the solution in case of proton excess, acid excess. Therefore, a buffer shows maximum activity at the pH which is numerically equal to the close to the pH value of buffer system. Traditionally, it is regarded that a buffer pair will show maximum buffering activity at a pH range equal to the buffer pK plus minus 1. In body fluid, we want to maintain the pH or close to 7.4, so that body fluids are need to have buffer with their pK value close to 7.4. If a weak acid is gradually neutralized by adding alkali at halfway of the neutralization, the weak and the concentration and its salt produced by adding alkali concentration become equal. So it is also right to say that buffer pair shows its maximum activity at half neutralization. An ideal efficient buffer is one which can resist the pH charge with equal capacity in either direction or addition of acid or alkali. A buffer can show its quality when the acid content of the buffer system is equal to the conjugate basic salt content, and means when pH equal to pK. Buffering capacity, buffer value. It is the amount of strong acid or strong base added to 1 liter buffer system with pH change by 1 unit. The more the amount added, the more is the buffering capacity. The body differs in order to decrease buffering capacity. Bicarbonate buffer system, protein buffer system, hemoglobin buffer system, phosphate inorganic buffer system. pK of the buffer system, content of the concentration of the buffer compounds, relative concentration of buffer base and buffer acid. Role of buffer as in our body living system. Carbonate buffer system. It is the principal extracellular buffer. Carbonate buffer system. Principal extracellular buffer. It consists of carbonic acid H2CO3 and its conjugate base, biocarbonate ion HCO3. It has pK value of 6.1 and normal body pH 7.4. Plasma bicarbonate concentration is 24 millimole per liter. Carbonic acid pH 7.4, plasma bicarbonate concentration is 24 mole per liter. Carbonic acid concentration is 1.2 millimole per liter with base of acid HCO3 and H2CO3 ratio 20.1, and the total buffer concentration is about 25 millimole per liter. Mechanism of action: when strong acid non-volatile is added, protons released from the acid are buffered by the base HCO3 and converted into H2CO3. So, strong acid replaced by weak carbon acid H2CO3 at the cost of HCO3 component that minimizes the fall of pH. H2CO3 thus formed breaks up to CO2 and H2O. When base of alkali, for example NaOH, is added, the base OH is buffered by the carbonic acid H2CO3, forming H2O and HCO3. So iron replace the strong bases of NaOH at the cost of H2CO3 component that minimizes the rise of pH. Advantage: this is why H2CO4 buffer is most important buffer. In spite of all limitations as a physiological buffer, bicarbonate buffer system is the most effective buffer in our body against all bases and all acid except H2CO3, because it is an open and system operates in open system that minimizes the components of this buffer system. H2CO3 and HCO3 can be independently regulated, increased or decreased when necessary by respiratory system and renal system respectively. To buffer acid, HCO3 is the converted to H2CO3, decreasing HCO3 concentration to buffer base of alkali. H2CO3 is converted into HCO3, decreasing H2CO4 concentration. 36% of buffering activity of ICF and 60% total body activity work both ICF and ICF and ECF. It accounts for 86% of buffering activity. Disadvantage: as a chemical buffer, it is rather weak buffer compared to the protein and phosphate buffer because of low pH value 6.1, which is far below the normal body pH 7.4. So advantage: HCO3 এর অ্যাডভান্টেজ এবং ফসফেট আর প্রোটিন বাফার থেকে ডিসঅ্যাডভান্টেজ। ফসফেট বাফার সিস্টেম HPO4. Mechanism of action. Advantage: as a chemical buffer, it appears to be a strong acid of pK value is closer to the body pH 7.4, but this advantage is offset by low content and closed end system. Disadvantage: as a physiological buffer, it is not an effective buffer in ECF because here its buffering capacity is very low due to the low content and concentration, 1 mole per liter. Protein buffer: it is the major intercellular buffer. A small amount is present in the blood and very negligible is interstitial fluid. It contains of acid and protein HPR and conjugate base or basic protein PR. Mechanism of action: when acid is added, proton released from the acid are buffered by the basic proton PR and converted into acid protein. So strong acid is replaced by weak acid and cost of basic protein components that minimizes the fall of pH. When base or alkali, for example NaOH, is added, the base OH minus is buffered by the acid proton HPR, forming H2O and basic protein. Protein buffers advantage: as a chemical buffer, it appears to be better than since its pK value is 6.4 to 7.8, range closely around the body pH 7.4. Disadvantage: as a physiological buffer, it is not as effective buffer in ECF because here its buffering capacity is very low due to its low content and concentration. Hemoglobin buffer system: it is the major buffer in RBC and consists of acid hemoglobin HHB or HHBO2 and their conjugate base or basic hemoglobin. So hemoglobin buffer system exists in hydrogenated form and hydrogenated or reduced from HHB. It has a pK value 7.4 to 6.6 to 7.8. Advantage: hemoglobin advantage. Hemoglobin buffer system. It is a major intracellular buffer in blood because of its high concentration and its pK value that range closely around the blood pH 7.4. The hemoglobin is a dominant buffer of blood with good buffering capacity, accounting for about 35% of blood buffering activity, which 6 to 7 times more than the plasma protein. Disadvantage: for effective buffering activity, it needs to cooperate with bicarbonate buffer system, ammonia NH3 buffer system. It consists of acid component NH4 and conjugate base or basic component NH3. It has a pK value of 9. Ammonia NH3 buffer system. It consists of acid component NH4 plus and its conjugate base or basic component NH3. It has pK value of 9. Alkali reverse. Advantage, disadvantage. Advantage: it is the principal buffer of urine, where it facilitates renal acid excretion. Disadvantage: it has no role in ECF and ICF. In proton deficit, in proton excess. Alkali reverse. It is equivalent to plasma bicarbonate concentration. Alkali reverse. Electrolytes are molecules that dissociate in water into the cation and anion equivalents and capable of carrying electric charge. Exercise on pH calculation. Chapter 2: Chemistry of carbohydrate. Definition of carbohydrate. Polyhydroxy organic compounds of 3 or more carbon having aldehyde CHO or ketone CO functional group. Aldehyde or ketone derivatives of polyhydric alcohol or the compounds which produce these derivatives are derivatives on hydrolysis. Classification of carbohydrate. Monosaccharide or simple sugar. General formula CN H2O N. The simplest form of carbohydrate which cannot be hydrolyzed further into further simple form of carbohydrate. These are 3 to 9 carbon compounds and serve as building blocks of all carbohydrate. Among the pentose and hexose are most important. For example, glucose, fructose, galactose, mannose, ribose and ribulose, etc. Disaccharide. Carbohydrate produced by condensation of two monosaccharide units by glycosidic bond. Sugars that produce two molecules of some or different monosaccharides on hydrolysis. For example, maltose consists of two glucose molecules. Lactose consists of one glucose and one galactose. For example, milk sugar. Sucrose consists of one glucose and one fructose. For example, table sugar. Oligosaccharide. Carbohydrate produced by condensation of 3 to 10 monosaccharides units by glycosidic bond. For example, maltodextrose, raffinose, blood group substance, etc. Polysaccharide. General formula C6H10O5, also called glycans. Polymer and monosaccharide composed of more than 10 monosaccharide units connected by glycosidic bond. For example, starch, glycogen, cellulose, monopolysaccharide, glycoprotein, etc. Sugar. Carbohydrates which are water soluble, crystalline and sweet in taste. For example, all monosaccharides and disaccharides. Non-sugar. Carbohydrate substances which are water insoluble and amorphous. For example, polysaccharides. Reduced sugar. Sugars which act as a reducing agent in alkali media. Presence of free anomeric carbon with free aldehyde or ketone function. group is responsible for this property of carbohydrate. All monosaccharides, maltose, and lactose are producing sugar. These tests of reducing sugar can reduce alkali CuSO4 solution. Positive Benedict test from oxazone crystal with phenylhydrazine, non-reducing sugar. Sugars have no free aldehyde or ketone functional group. Their functional groups are usually engaged in glycosidic bond formation. Sucrose is non-reducing sugar. Sucrose is composed of glucose and fructose. Glucose contains aldehyde group with the first carbon C1 and fructose contains ketone group with the second carbon C2. From sucrose, glycosidic bond is formed between C1 of glucose and C2 of fructose. So neither of the two functional groups is free to show the reducing property, so that the sucrose is non-reducing. Importance of lactose. As a component of milk, it acts as a dietary carbohydrate to provide energy. In congenital deficiency of lactase, lactose cannot be digested, leading to lactose intolerance. Classification of monosaccharides. Monosaccharides is classified on the basis of the functional group they contain. Aldose, if contain aldehyde group, CHO as functional group. Ketose, if contain ketose group K as functional group. It can also be classified on the basis of number of carbon they contain. Triose, if contain 3 carbons. Tetrose, if contain 4 carbon. Pentose, if contain 5 carbon. Hexose, if contain 6 carbon. It is more acceptable to classify monosaccharides taking into account both the concepts and simultaneously as given below. Generic name: carbonol, aldose, and ketose. Triose, glyceraldehyde, dihydroacetone. Triose, erythrulose. The first one is aldose and the second one is ketose. Pentose, ribose, xylose, arabinose. Ribolose, xylulose. Hexose, glucose, galactose, mannose, fructose. Primary alcohol group CH2OH of monosaccharide remains attached with the terminal carbon, which is 6th carbon of the hexose, 5th carbon of the pentose, 4th carbon of the tetrose, and 3rd carbon of the triose. Penultimate carbon of a monosaccharide is the carbon adjacent of the primary alcohol carbon, which is the 5th carbon of the hexose, 4th carbon of the pentose, and so on. In aldose, the aldehyde functional group is usually attached with the first carbon, and in ketose, the ketone functional group is usually found in the second carbon.
Homopolysaccharide বা homoglycan, polymer of similar type of monosaccharide connected by the glycoside bond. Starch. It is the polymer of glucose found in plants as the storage from the carbohydrate. It is obtained entirely from plant sources. There are two types of starch, amylase and amylopectin. Glycogen. It is the polymer of glucose found in animal and human as the storage from the carbohydrate. Dextran, cellulose and inulin. Heteropolysaccharide or heteroglycan, polymer of different variants of monosaccharide unites to their derivatives connect by the glycoside bond. Mucopolysaccharide or glycosamide glycans, carbohydrate part of glycogen. Amylase, polymer of 200 to 100 alpha D glucose unites and represent 10 to 20% of the starch, spawning water soluble and straight chain structure. Amylopectin, polymer of few thousand of alpha D glucose unites that represent 80% of starch, water insoluble and branched chain structure. Glycogen, polymer of D glucose unites or obtained entirely from animal source. It resembles amylopectin. It shows branching, but number of branches are even more than amylopectin. Common source of glycogen: liver glycogen, muscle glycogen. Dextrin, polymer of D-glucose produced by parietal backbone or hydrolysis of starch. This enzyme alpha amylase causes the random cleavage of glycosidic bonds well inside the starch molecule, produce the different glucosaccharide fragment called the dextrin. Dextran, polymer of alpha D-glucose, units formed by the microbes, bacteria, and yeast. Branch structure non-digestible or colloid in nature. Clinically, dextran used in plasma expander to prevent the hypovolemic shock during major surgery or other condition associated with fluid loss. Following intravenous infusion of dextran, it is retained within blood vessel and increases plasma colloidal osmotic pressure that draw water within the blood vessel from the extravascular space to maintain blood volume. Cellulose, polymer of alpha D glucose and strange chain structure, derived from plant source, vegetable, fruits, etc. It is non-digestible in human, so given no energy. Inulin, polymer of fructose and water soluble. Low molecular weight, about 5,000, and found in onion and garlic, etc. It has no dietary importance but used for GFR measurement. Different between the amylase and amylopectin. Amylase is a starch, amylopectin is a starch. Represent 10 to 20% of starch, represent 8 to 90% of starch. Low molecular weight, high molecular weight. Composed of 200 to 1000 glucose molecules, composed of few thousand of glucose molecules. Springly water soluble, water insoluble. Unbranched structure, strange chain, highly branched. Give blue color with dilute iodine solution. Give reddish violet color with the dilute iodine solution. Difference between the glycogen and starch. Feature of glycogen and starch. Source হচ্ছে animal source, starch হচ্ছে plant source. Rice, potato, wheat. Structure: highly blindless, less branched amylopectin or unbranched amylase. Molecular weight 10 to 40 lakh, about 5 lakh. Color with iodine solution, give deep red color, gives reddish violet color. Importance: storage from the carbohydrate in human, main dietary carbohydrate in human. Types of mucopolysaccharide or glycoaminoglycans. Types such hyaluronic acid, possible type, connective tissue, synovial fluid, etc. Chondroitin, SO4A, cartilage, bone, tendon, etc. Condon as bone, skin, blood vessel, etc. Condon SO4C, cartilage, bone, tendon, etc. Keratin SO4, keratin surface, cartilage, cornea, etc. Heparin sulfate, cell sulfate, basement membrane. Heparin mast cell. Hyaluronic acid, produced by some bacteria, depolymerase and liquefy hyaluronic acid to reduce the viscosity to tissue and thereby the facilitate spread of infection. Isomerism and sugars. Monosaccharide usually shows two types of optical stereomerism, DL isomerism and alpha B anomerism. D alpha isomerism and D isomer, D L isomer. D and L isomer are optical stereo isomers produced by the isomerization of group containing carbon CH2OH. In case of glucose and penultimate carbon is the fifth carbon because its 6 carbon contain primary alcohol group. The orientation of H and OH groups around the penetrant and carbon determines whether the sugar bonds of D rise and D series or L series. Where the OH
is on the right, the sugar D is isomer. When it is on the left, it is L isomer. In DLL varieties, the group in other carbon atoms, for example, second, third, and fourth carbon atoms of glucose, are totally reversed, so they are the mirror image of each other. These sugars are most common in nature. Our body can metabolize only D sugars, not L sugars. 2. Alpha beta anomerism and alpha anomer beta anomer. Anomeric carbon, carbonyl carbon of sugar is the carbon which contains the functional group aldehyde and ketone group. In case of glucose or galactose, it is the first carbon, and in case of fructose, it is the second carbon. Anomeric carbon is symmetric and straight chain structure form. In case of glucose or galactose, it is the first carbon, and in case of fructose, it is the second carbon. Anomeric carbon symmetric in a straight chain structural form. Properties of carbohydrate in reference to monosaccharide and disaccharide. Physical properties: water soluble, crystalline, sweet in taste, and typically active. Chemical properties: act as reducing agent in alkali media. For example, glucose reduce cupric ion of CuSO4 to cuprous ion in alkali media known as positive Benedict test. Oxidized to sugar acid. For example, aldonic acid. If functional group containing anaerobic carbon is oxidized, for example, glucose oxidized to gluconic acid. Uronic acid. If primary alcohol group containing carbon is oxidized, for example, glucose is oxidized in gluconic acid. Saccharic acid. If both anaerobic and primary alcohol carbons are oxidized, for example, glucose is oxidized to glucosaccharic acid. Reduced to alcohol, for example, sorbitol, mannitol, dulcitol, ribitol, glycerol. Produce oxazone crystal with penyl hydrate, for example, glucosazone produced by glucose, maltosazone produced by maltose, etc. Produce glucoside by condensation with alcoholic group of another substance. Forms ester with organic or inorganic acid, for example, glucose 6p. Liver uses glucuronic acid for its conjugation and detoxification function. Mannitol is an osmotically active solute which is filtered but not reabsorbed from renal tubule. Therefore, mannitol can cause forced diuresis, to its clinically used to treat cerebral edema by forced diuresis. Sorbitol does not readily diffuse out of cell. As it accumulates in cell, it causes osmotic damage to intracellular components, especially in neurons, and leads to develop neuropathy and cataract. Glucosidic bond. Monosaccharides are connected with each other through glucosidic bond to form glucosaccharide, polysaccharide, and other complex carbohydrate. Carbohydrate can also be connected with other non-carbohydrate alcoholic substance through glycosidic bond and from glycosides. Glycosidic bonds between sugar are named according to the number of connected carbons and also regard to the position of anomeric hydroxyl group of the anomeric carbon participating in the bond. For example, C1 and C2. In polymers of alpha D glucose, for example, a starch glycogen, glucose units are connected by alpha A for glucosidic bond, whereas in polymers of BD glucose, for example, cellulose, glucose units are connected by B1 for glucosidic bond. In humans, enzyme for carbohydrate digestion can break alpha 1 for glucosidic bond, not the B variety. So cellulose is not digestible for us. Glycosides.
Glycosides are substances produced by the condensation of the cyclic monosaccharide with alcoholic group OH of another second compound. Formation of the cyclic monosaccharide involves the functional group containing anomeric carbon, and it may be the cyclic Hemisexual. If alders are cyclic, hemiketal eat ketones. Second compound providing hydroxyl group may or may not be monosaccharide. If it is monosaccharide, the resulting glycosides become disaccharide. The non-carbohydrate substrate providing hydroxyl group to make glycosaccharide are collectively called a glycon. Common a glycons are methanol, esterol, glycerol, phenol, etc. Cyclic forms or hemocentric hemiketal of monosaccharide are unstable and provide potentially free aldehyde or ketone group because in solution they remain in equilibrium with their respective straight alkyl chain from the hydroxyl group of the anomeric carbon of monosaccharide in cyclic form again reacts with another alcohol group of a second compound of to form the stable cyclic structure called the acetal if aldose or ketol if ketose. Structurally and conceptually, these acetal and ketal substances are known as glycosides. D-alpha D-glucose hematocrical cyclic form and D-glucose acetal cyclic form. Common glycosides are the cardiac glycoside Zizdalis. It contains esterol as glycon. It inhibits sodium potassium bond and used in heart failure treatment. Streptomycin, erythromycin, they are used as the antibiotic. Oubutin,
Oubutin.
Euben, it is obein, obein. Obein is used as the inhibitor of sodium potassium pump. Prolihisine, it is used to block glucose absorption in intestine. The complex carbohydrate, aminoglucose, sugar and amino group attached usually in the second carbon glycosamine, glucose carbon NH2 galactosamine, mannose found in glycoprotein, glycolipid and mucopolysaccharide, and acetaldehyde amino sugar with sodium hydroxyl group at its second carbon and acetyl group attached with NH2 group found in glycoprotein, glycolipid and mucopolysaccharide. Acetylated glycosamine, glucose C2 NH2 CH3COH, sialic acid and acetyl uramic acid or NANA. It is an acetyl monosamine with pyruvate attached at its first carbon. It is found in glycoprotein and glycosides. Mannose, CH2 NH2 CH3COH, pyruvate. Mucopolysaccharides, carbohydrate part of the glycoprotein. The mucosubstance, carbohydrate of mucosubstance composed of carbohydrate and protein. Whitish, very viscous and slippery, and strongly negative and hydrophobic. Types of mucosubstance: glycoprotein, mucoprotein. Here the protein is the dominant part, carbohydrate is the minor part, and carbohydrate part is usually a short oligosaccharide chain. Proteoglycans, peptidoglycan. Here protein represent minor part, but carbohydrate represent dominant part up to 95%, and the carbohydrate part of the proteoglycan is known as the mucopolysaccharide and glycosamine glycan. Function: importance of the mucopolysaccharide and glycoaminoglycans. Compound of the extracellular matrix, synovial fluid and vitreous humor, mucus, etc. Act as biological lubricant to provide protection against the mechanical injury and microbial invasion. Mucus of the respiratory tract, GIT, urogenital tract contains the mucosubstance and protect the body from the microbial invasion. তুমি কালকে কটায় যাবে যে 5টায় বেরোবো? Alimentary tract allow easy slippage of food from mouth down to intestine. Mucous substance in mucous substance in joint space and in different potential space prevent the mechanical injury. Function of glycoprotein, component of the extracellular matrix, count substance of the connective tissue, act as biological lubricant to provide the protection against the mechanical injury and the microbial invasion. Mucous substance in joint space and in different potential space prevent the mechanical injury. Cellular recognition or cell-to-cell interaction serve as cell surface receptor and cell surface antigen blood group substance. Difference between the mucopolysaccharide and glycoprotein. Mucopolysaccharide long chain heterophosphorsaccharide, short chain heterophosphorsaccharide, mostly branched, consist of repeating disaccharide units made of amino sugar and glycosamine and acid sugar glucuronic acid, consist of hexose acetyl amino derivatives of hexose, pentose and salic acid, contain uronic acid and glucuronic acid but no salic acid, contain salic acid but no uronic acid. Biological importance function of carbohydrate and glucose. Chief source of energy. Glucose derived from dietary carbohydrate is the main fuel of the body. Glycogen produced from glucose acts as important storage form of energy in body. Helps in protein and fat metabolism. Helps in nucleic acid synthesis by providing ribose, pentose sugar. Act as protein and fat supper. Presence of glucose spare protein and fat from oxidation catabolism. Pressure for synthesis of lipids, amino acids, glycolipids, proteoglycans constitutes the structural component of biological membrane, intercellular ground substance and biological lubricant. Involved with detoxification of toxic substance in liver by providing the glucuronic acid. Importance of cellulose. Advantage: prevents of constipation and maintain regular bowel habit. Facilitates the cholesterol excretion. Keeps biological importance of carbohydrate and glucose. Chief source of energy. Glucose derived from dietary. Shubir, কি নাম বলছে সুবীর?
Monomucopolysaccharide MPS, glycoprotein, long chain heteropolysaccharide, short chain heteropolysaccharide, mostly branched, consist of repeating disaccharide units made of amino sugar, for example glucosamine, and acid sugar, for example glucuronic acid. Contain uric acid, glucuronic acid, but contain uronic acid, contain glucuric acid, but no salic acid. Glycoprotein, short chain heteropolysaccharide, mostly branched, consist of hexose, acetyl amino derivatives of hexose, pentose and salic acid. Contain salic acid but no uronic acid. Biological importance of carbohydrate. Glucose, chief source of energy. Glucose derives from dietary carbohydrate, is the main fuel of the body. Glycogen produced from glucose acts as important storage for energy in the body. Helps in protein and fat metabolism. Helps in nucleic acid synthesis in providing ribose. Acts as protein and fat separator. Presence of glucose spare protein and fat from oxidation catabolism. Precursor for synthesis of lipid, amino acids, glycoproteins and proteoglycans. Consist of precursor for synthesis. Presence of glucose spare protein and fat from oxidation catabolism. Precursor of synthesis of lipid, amino acids, glycoproteins and proteoglycans. Constitute the structural components of biological membrane. intracellular ground substance and biological lubricant, involved with detoxification of toxic substance in liver by providing glucuronic acid. Importance functions of cellulose. Advantages: prevents constipation and maintains regular bowel habit, facilitates cholesterol excretion, keeps serum cholesterol low, and reduces the risk of coronary artery disease, prevents the risk of obesity, diabetes. Importance of function of cellulose: risk of obesity, diabetes mellitus, and chronic cancer. Disadvantages: it prevents the intestinal absorption of minerals, ferrum, zinc, calcium, etc.
Chemistry of protein. Amino acid is the amino group containing carboxyl acid. আমার কিডনির অসুখ মনে হয়েছে ওর each amino acid has an acidic carboxyl group, a basic amino group, and a distinct hydrocarbon side chain air group. An H2 group, COH group, and distinct side chain are bound to the alpha carbon. General structure of amino acid: CH3, CH2, and CHCOH. So amino acid has a central acetyl alpha carbon to which following four different group are atoms are attached. Amino group: it isoelectric pH is 9, so at body pH 7.4 it exists as the protonated from NH3. Carboxyl group is isoelectric pH is 2, so at body pH 7.4 it is exists as diprotonated from. Hydroxyl atom side chain R. Amino acids differ from each other only with respect to the side chain, so the nature of this side chain determines their properties and function in protein. In total, there are 20 different amino acids in human body, and all body proteins are constructed from this basic set of 20 amino acids, which are specific by genetic code. So they are also called the primary amino acid and standard amino acid. Amino acid participating in body protein synthesis are alpha type because the amino group is usually attached with the alpha carbon and placed in left side with respect to the spatial configuration. Alpha carbon with NH2 group on left side and side chain. All body amino acids except glycine have asymmetric alpha carbon, so amino acid can produce optical isomers with optical activity. Exceptionally, glycine does not have any side chain. Here the R is replaced by the another hydrogen atom. There its alpha carbon is symmetrical. Conventionally, name of amino acid are abbreviated by the first three letters of the name. The serene exception of this convention is practiced only for
Triphosphate TRP, isoleucine LLU, asparagine ASM, and glutamine GLNU. Classification of amino acid based on a structure of side chain R and their reaction in solution. Acidic amino acid: monoamino dicarboxylic acid, negatively charged at body pH. They contain one amino group and two carboxylic groups. For example, aspartic acid ASP, glutamic acid GLU. Basic amino acid: diamino mono carboxylic acid, positively charged at body pH. They contain two amino groups and one carboxylic group. For example, different biomolecules and their building blocks. Monomers present in biological system can be broadly classified into crystalloid, amicron, and colloid, submicron, depending on their size. Crystalloid are substances with size 1 nanometer, less than 1 nanometer, which can pass through semi-permeable membrane. For example, electrolytes, minerals, glucose, amino acids, etc. These are crystalloids. Colloids are substances with size 1 to 100 nanometer which cannot pass through semi-permeable membrane. For example, protein, glucose, starch, etc. 90% of the organic matter of living tissue is colloid. Microns are solutes having size more than 100 nanometer and they form unstable emulsion or suspension with water. Important plasma crystalloids are glucose, amino acids, urea, electrolytes, and minerals. Important plasma colloids are plasma protein. Commonly, dietary colloids are protein, starch, and cellulose. Difference between crystalloids and colloids. Crystalloids size 1 nanometer and not seen by ultra microscope. Size 1 to 100 nanometer and seen by ultra microscope. Can pass through semi-permeable membrane. Cannot pass through semi-permeable membrane. Crystalline and dialyzable. Amorphous and non-dialyzable. Form homogeneous solution, true solution with water. Form heterogeneous solution called colloid system with water. Osmotically very active and exert high crystalloid osmotic pressure in water. Osmotically less active and exert less colloid osmotic pressure in water. Determine water movement across the cell membrane. Determine water movement across the cellular membrane. Cell colloidal system solute is regarded as the dispersed phase and solvent is regarded as dispersion medium. Colloid definition: substance having molecular size, atomic size 1 to 100 nanometer which cannot pass through semi-permeable membrane. Types of colloid: hydrophilic colloid. Practically all colloids of living systems are hydrophilic. These are solvent having loving and have affinity to water. They are easily solvented or hydrated where a shell of water molecule is formed around them. For example, protein, polysaccharide, ball salt, etc. These are types of colloid: hydrophobic, lipophilic colloid, hydrophilic, and now hydrophobic. These are solvent hating, have no affinity to water. They are kept in solution by hydrophilic colloid absorbed around them. For example, colloidal gold, conjugated bilirubin, etc. Properties of colloids. Brownian movement. It is the continuous, rapid, and hazardous movement of colloid particles in solution due to the uninterrupted buffering or colloid particle given to solvent molecules. It is a sort of perpetual game of molecular billiards. It is seen under ultramicroscope. Tyndall phenomenon. When a beam of light is passed through a colloidal solution and observed at right angle, the track of light becomes visible at white line due to the dispersion of light rays by the colloidal particles. In true solution, this phenomenon is not true, so true solutions is particularly clear. Electrical phenomenon. They carry electric charge, positive or negative. They have a definite isoelectric gauge at which they behave as Zwitter ion, become least soluble and may precipitate out. They undergo electrophoresis by which colloidal particles are separated from each other. Surface phenomenon. Colloid particles have larger surface area per unit mass. They show increased phenomenon of absorption and interface tension. Importance of colloid and colloidal osmotic pressure (COP). Colloids determine the colloidal osmotic pressure in plasma, which is needed to hold water within vascular compartment. If plasma colloid and COP decrease, water comes out of blood vessels to make edema. If plasma colloid and COP increase, water enters the blood vessels from extravascular space to expand blood volume. Suspension. It is a heterogeneous system of a solute with water where solute dispersed phase which is more than 100 nanometer. For example, antacid suspension RBC in plasma, etc. Emulsion. It is a liquid heterogeneous system produced by dispersion of liquid droplets to another liquid in which it is insoluble. One liquid behaves as dispersed phase solute and the other behaves as dispersion medium. Here, size of the dispersed phase solute is 100 to 100 nanometer. For example, cod liver milk emulsion in fat in water. Emulsified agent. These are substances which stabilize an emulsion. Dispersed droplets solutes of emulsion tends to coalesce due to surface tension, interfacial tension, but emulsifier being concentrated at the interface between dispersed droplet solutes and the dispersion medium solvent reduced the surface tension and provides the tendency of the spores droplets to coalesce. For example, bile salt acts as an emulsifier to stabilize emulsion of fat in water. Alpha beta anomerism and alpha anomer beta anomer. Anomeric carbon. Carbonyl carbon of sugar is the carbon which contains the functional group aldehyde or ketone group. In case of glucose or galactose, it is the first carbon, and in case of fructose, it is the second carbon. Anomeric carbon is symmetric in straight chain structure form. Monosaccharides possess tendency to make cyclic structures involving aromatic carbon. In case of glucose, aldehyde group of first carbon can condense with the OH group of fifth carbon to make the cyclic structure. In this process, the anomeric carbon, which was symmetric in straight chain form, now become asymmetric in cyclic form due to the asymmetric structure. Anomeric carbon attains the potential to produce isomers called anomers. Anomers are optical stereomers isomers produced by isomerization around the anomeric carbon of monosaccharides in cyclic structure form. In this form of, if OH group of anomeric carbon lies on a straight side, it is a alpha monomer. If it is on the left side, it will be a beta monomer. Optical activity of different sugars. Since monosaccharides contain asymmetric carbon, they are capable to produce optical isomers and to show optical activity by rotating the plane polarized light passing through their solution either to right called dextrorotary isomers or to the left called revelatory isomers. Inverted sugar. Sucrose is dextrorotary with optical activity plus 66.5 degrees. In hydrolysis, sucrose produces D-glucose with optical activity plus 52.5 degree and D-fructose with optical activity minus 92 degrees, resulting optical activity of the mixture of D-glucose and D-fructose finally becoming minus 20 degrees, which is laboratory. Dextrorotary optical characters of sucrose on hydrolysis is invented to the laboratory character. This change in rotation is known as inversion, and so the name is invert sugar. Importance Important dietary carbohydrate: starch, rice, potato, wheat, etc. Lactose, milk and milk products. Sucrose, sugar, cane sugar. Cellulose, vegetables, fruits, etc. Difference between lactose and sucrose. Lactose known as milk sugar. Sucrose known as cane sugar, composed of D-glucose and D-galactose, composed of D-glucose and D-fructose. Non-invert sugar, invert sugar. Reducing sugar, non-reducing sugar. Form oxazo crystals with phenylhydrazine. Do not form oxazo crystals with phenylhydrazine. Can be synthesized in lactating breasts. Cannot be synthesized in human. Lactose sucrose. Hydrolyzed by lactase. Hydrolyzed by sucrase. Priorities of carbohydrate in reference to monosaccharide, the disaccharide. Physical properties: water soluble, crystalline, sweet in taste, and optically active. Chemical properties: act as reducing agent in alkali media, for example glucose, reducing cupric ions of CuSO4 to cuprous ions in alkali medium, known as positive Benedict test. Oxidized to sugar acid, for example iodic acid. Its functional group containing anaerobic carbon is oxidized. For example, glucose is oxidized to gluconic acid. Uric acid. If primary alcohol group containing carbon is oxidized, for example glucose is oxidized to glucuronic acid. Saccharic acid. If both anaerobic and primary alcohol carbons are oxidized, for example glucose is oxidized to glucosaccharic acid. Reduced to alcohol, for example sorbitol, produced by reducing glucose to fructose. Mannitol, produced by reducing of mannose to fructose. Dulcitol, produced by reducing of galactose. Ribitol, produced by reduction of ribose. Glycerol, produced by reduction of triose. Produced oxazone crystals with phenylhydrazine, for example glucazone, produced by glucose. Maltazone, produced by maltose, etc. Produce glucosides by condensation with alcoholic group of another substance. Form ester with organ or inorganic acid, for example glucose 6p. Liver uses glucuric acid for its conjunction and